Assalamualaikum warahmatullahi and good afternoon for everyone. Can you hear me? Okay. Please refer to the chat box. I've given the link. For you to access the notes and also the data. And for your information, the data, if just only can be accessed by the students or the staff within University Malaysia Sarawak. I believe some of you are from outside from University Sarawak. You try to email me later, and I will email you back the data and the notes. And then another thing is that this session will be recorded, and I will upload the full video in my YouTube. You can follow my YouTube channel later, and I will update this video in my YouTube channel. Okay. Okay. Today I would like to share you about a brief about the survey data analysis lah. And actually this session I dedicate to my final year student project. Okay, but then I also invite my session today to the public who interested to want to know more lah. Okay, so let us start lah. Okay, my session today. For my students, please please give full attention to my lecture today. Okay, first of all, actually related to the survey data analysis, right? So actually, if we want to publish a good research, we need to understand the two things about the survey data analysis, especially when we want to how can I say, we want to do not to say a perfect efficient and effective analysis lah. Okay, so the first thing is that normally in the literature when we collect the data, the survey data, got two types of the survey data. The first one is we collect the data and absolute data. What does it mean by the absolute data here is that, example, if we ask about the income of an individual, then the data that we expect from them to give to us is an absolute data, meaning to say, like example, what is the income, the monthly income that they earn. So they will state there, right, example like 150, 159, something. Okay, that is what it means by absolute. On the other way around, we also can collect the data by class of income. Say we come up with the range 1,000 to 2,000, okay, 2,000 to 5,000, and then they will choose at what range is the income. That one based on the scale. Okay, so when we use this kind of data, it actually gives an impact, or it actually how can I say, it actually can give can influence how perfect is our estimation. So we need, meaning to say that here we need to choose a correct method based on the data that we have. This is what it means. Secondly, normally, especially if let's say we want to collect the data related to the feeling or the satisfaction, okay, the factor or the variable that we need to collect the data in terms of the feeling, and then as I mentioned just now, the feeling, the satisfaction, then we come up with the rank, the scale. How happy are they? They will choose 1 to 6, right? So that scales actually have an instrument. Example, we have a factor 1. To measure the factor 1, we come up with 6 instruments. Okay, so this 6 instrument in terms of the scale. Example, we provide them a scale 1 to 6. So all of our data in the end, it just only around 1 to 6, 1 to 6, and 1 to 6, and so on. So the first question is that we need to answer whether the regression analysis like OLS is sufficient or not. Because the variety of our data letter is just only 1 to 6, a mix of 1 until 6. That's the first one. Second, how are we going to, let's say, just now I mentioned to you, the instrument, 6 instrument to proxy one factor. So we have 6 instruments here. The 6 instrument here, how can we convert become one factor? Okay, this is what it means here in this slide, the variable construction. So in this case, actually, since we have a limitation in terms of the nature of the data, as I told you about the data about the filling 1 to 6, how can we merge 6 instruments to approximate one factor? Either we average it, this is what we call as mean, okay, or we use other details or more advanced method to present one value for one factor. This is what it means. So basically, in a standard nature, in the standard studies, normally people just use mean. Same goes to if let's say you are using SPSS, there is a tool to average the 6 instruments to compute one factor. After this, I will show you the example. This is one of the examples. So what is the disadvantage for us to use the what is the advantage for us to just to simply average that one, average the instrument. Okay, Yulaika, please mute. Okay, so actually if let's say we pull it, mean if we pull it become one variable, meaning to say that we actually average all in one factor. So meaning to say that there is a possibility for us to have some missing information. This is what it means if let's say we mean it. So to come up with a good research or to reduce this missing data, missing information, we have another method to use that is more efficient than to pull it. This is what we call as PCA, Principal Component Analysis. Okay, today I will show you how to do a Principal Component Analysis instead of to use the technique of to pull all instruments become one factor. Okay. Secondly, so normally I believe that you are very quite familiar with the OLS. Okay, but then the OLS here is very weak. If let's say we want to analyze the data that use that the data that we are collected in terms of scale. Okay, the data that we have, example just now I mentioned to you, let's say we provide a scale 1 to 6. So the data that we have is just only revolve 1 to 6, a mix of 1 until 6. So for OLS, it is very much difficult for OLS to capture the nature of the data, and in the end, our estimation is not that robust. So that's why, if let's say your data is in terms of the scale, or else your study is all about the feeling, okay, then something that is not something that we convert become numbers, then OLS is not really preferable. So you need to use structural equation model. These are the things that you need to understand. So basically for today, I will show you how to do the construction, the variable construction, okay, in a proper manner to use STATA, and also the regression analysis. Definitely, I will show you how to run OLS and SAM. Okay, that is the introduction. Okay, so for today, assume that uh, this is our model. Okay, today I'm gonna use the example of this model. Okay, in the data, in the link, you can definitely access to the data and also the nodes. Okay, if you refer to the data that I've provided, okay, I've labeled the data for dependent variable named as y. So the instrument for y got 7 instruments. Okay, for independent variable, I've provided to you XA. That one for independent variable got 8 instruments. Okay, the last one is the control variable age, income, and education. So age, income, and education, I put in scale. So I collected the data to ask about the age and what range, which group then goes to the income and education. So it's in terms of the range nature of the data. Okay, all right. So now, as I told you, since the independent variable y example, we have 7 instruments, how we gonna construct the variable of y derived from 7 instruments? This is what it means. Then we go to the independent variable. We have 8 instruments, and then the control variable got no instrument because I straightforward asked about the age, income, and education because it's not related to the feeling. Okay, if let's say it's related to the feeling, then we need a lot of the question, a type of question, a lot of the question to ask them to give us a picture about the feeling, about their feeling. So about the age, income, and the education is very straightforward lah. No need for us to ask them to ask them many questions. Okay, example. This is the first step. Okay. So the first thing is that what we need to do is that we need to check, we need to identify statistically whether our data, the sample of our data is adequate or not. So what test that we can do is this. Okay, we have Bartlett and also KMO. Okay, so if you use this data, this is the code, this is the command that you can type there. Take the test y1 until y7. So y1, y2, y3, y4, y5, y6, y7 is the instrument. Okay, the instrument, and then then the data will give you the output of the result. This is the output of the result. Okay, so what does it mean by this example? Okay, this is the elaboration. Okay, the determinant of correlation matrix is 0.235. What does it mean? Okay, this statistic tries to confirm to us the seven instruments that we use to measure or to approximate y. Actually, the score is this. What does it mean? If let's say value close to 0 means that high multicollinearity. If let's say value closer to 1, acceptable. So in this case, 0.2 is moderate, meaning to say that the data here seems like correlated among them. So if let's say example, it's very close to 0, it means it's correlated among themselves, meaning to say that there is an element of a sort of a double counted problem. So in order to overcome this problem, you need to increase your sample. So in this case, why it's only 0.2? It is because for demo, I just provide you about 80 sample. So if let's say you can have 100 or 300, I believe that the result will be improved. Okay. Okay. Bartlett. Okay. The Bartlett is a test. Okay. Same with this, the determinant of correlation metric, but the Bartlett will give you will give a test more to, how can I say, in terms of hypothesis development. As you can see here, what is the rationale here indicating that correlation exists among the variable. If let's say the value is not is significant in this case, we can reject the null hypothesis to say that even though the correlation metric here to say that the value is just 0.2, not satisfying, acceptable but not satisfying. But then it's support, but we must support with this test to say if even though it's just satisfying, but we still can reject the null hypothesis, meaning to say that we still can accept. Okay, we still can accept that one. How can I say? Accept this multicollinearity element. Okay, through this test. This is the good thing. This is one of the good tests. If let's say we want to confirm statistically whether our samples are free from multicollinearity. Okay, the last one, KMO. Okay, the KMO is a sample to confirm whether the how can I say, the 7 instrument that we use adequate or not to represent Y. Okay, this is the standard. In this case, my score is 0.766. Okay, it's still acceptable according to this score. Okay, if you want to improve further, then we need to increase more. What can I say? Samples. Okay. Okay. If we're done with the sample adequacy, all things okay, you need to repeat the same step to try to test XA just now, the independent variable. Okay, that we have here at instrument. You repeat the same procedure, try to look at how about the result for XA, our independent variable, see how, okay, how's the result. So if all okay, then you can proceed to reliability test. So reliability is one of the most important tests lah. If let's say we want to do a survey data analysis, especially if we use a scale. If you use the information that the information that we are collected, we provide a scale number. Okay, okay, this is the step lah. Okay, the reliability, the compile file. Okay, this is the code. Okay, I highlight in red color here, definitely will get this number. So things that I want to highlight here, the sign here. If let's say the sign here all consistent, like in this case, all positive, meaning to say that all instrument here, all 7 instruments here is reliable. Okay, okay, reliable. But then example, I will give you another example here. So this for independent variable, you look at this XA1 until XA8. You look at this, some of the instrument here negative. So for this, the sign should be consistent, either all positive or all negative. How to overcome it? You use this command so that the negative instrument can become positive here, mathematically. But if let's say like example, if the sociology, the psychology field, they will check back the questionnaire. How actually the questionnaire, how did the respondent respond to their questionnaire? It is not simply to use this kind of technique, okay, to fix the problem of the data. Okay, but then they will check in depth what is the problem of the data, what is the problem of that kind of questionnaire. But mathematically, this is one of the remedy to improve the data so that the signs are positive. Okay, that's what we mean. So we want all of our how can I say, all of our instrument here is have the same nature, so that we can use all of these 8 instruments to approximate independent variable. So if you look here, right, we use the new code, the new variable for things that have a negative value. Okay, like this. You can try it. Okay, this I provided here the, how can I say, what is this? The elaboration for each test. Okay, example how to the compa alpha. The value here is 0.4, and then this is the explanation. Okay, so the law for compa alpha is this. So in this case, the value for test for alpha is 0.7, 0.7017, and then it's still acceptable. Okay, meaning to say that all of the sample here, the instrument here is acceptable statistically. Okay, that's what it means. Okay, now if let's say all of these 3 tests are testifying good, okay, then we can proceed to construct the variable. Yeah, this is what I mean. So just now I mentioned to you example like Y. Y, we have 7 instruments. How these 7 instruments we can boiling down the numbers become one single number. This is what I mean. How to merge, how to pull it in an accurate way to become one single number. This is what it means. Okay, but then you need to make sure the 3 tests just now are all in good fit. Okay, but then we can proceed to construct the variable. So the thing that I want to show you the technique instead of to use mean, I've explained to you the disadvantage if let's say we use mean or we pull all these instruments. Okay, or in a scientific, in other words, we can call it to use mean technique. It is unweighted. So if let's say to use PCA, it's more to weighted approach. So why? So simply, actually, the topic for PCA is quite long. You can explore it on your own. But then basically, what can I deliver to you in a simple way? PCA is actually a method that will give you a weighted number, a suitable weighted number to merge all of the instruments become one single number. This is what it means. Okay, and then mathematically, when the software look at all of the observation, all of the sample, definitely they will come up with the suitable weighted number for each instrument rather than you simply how can I say, you say simply pull it become one single number. Okay. Secondly, if you use mean technique, if you pull all 7 how can I say, if you pull all 7 instruments, okay, become one single number, you need to make sure that your instrument here consistent with the other instrument, meaning to say that if let's say you use 7 instruments for dependent variable, for independent variables, all independent variables must have 7 instruments. You need to be consistent. But then if you use PCA, it is not necessary for you to have same numbers of instruments. Example, in this case, my Y have 7 instruments. My independent variable have 8 instruments. It would be fine. If let's say another variable, you have 4 instruments, it's also fine. As long as you use PCA technique to construct the variable. Okay? So this is the command. If you use the STATA, you try the data that I've provided, and then you type this command. The second one is this. You need to type this command first, and then the STATA will give you this. This number is actually the way STATA to compute and consider suitable weighted number for each instrument. Okay, actually to learn each numbers. Okay, each component of this actually is quite complicated. In a simple way, this is the way we calculate to know a suitable weighted numbers. This is what it means. So in the end of this technique, we just need to put this kind of command. This is the command that we want to uh, merge all 7 instruments become one single number, as I mentioned to you, y just now. Okay, predict y, comma, score, then the STATA will give you the value for y while considering all 7 instruments using an appropriate weighted number. Okay, this is what it means. Okay, for the this one independent, and for this one it's for independent. You use the same technique here. Okay, so you can get the variable just now I mentioned to you. Now you can get STATA will provide you one single number for y here and x. You see, so you have 7 instruments for y just now. Now become only one single number. Same goes to xa. Just now we have 8 instruments. So now we have one single number. This is the value for y and the value for xa using PCA technique. Okay. So later when we run the analysis, regardless to use the regression or to use the SEM, structural equation model, we will use this number, not the data from instrument just now. The data of instrument data just now, we just have 1 until 6, 1 until 6, and 1 until 6. This is one of the advantages, okay, to use PCA. Okay. Okay, now, once you got the data, once you have constructed your variable, once you have constructed the variable, you can proceed to do analysis regardless to use the OLS or the SEM. Example, I showed you the OLS first to use data, but in this case, some of it I use data and some of it I use EViews. Okay, example, to use data, this is the chord. Okay, Y is the dependent and XA is my independent. H, education, and income is my control variable. So this is the result from OLS. Okay, as you can see here, this is the coefficient and the significancy. If you look at this, my XA is not significant. So my education and income is significant with negative. Okay, and then you can also I can look at F-test. Okay, but then for OLS, it is important for us to make sure the, how can I say, the model or estimation is blue. Okay, what does it mean by blue? This is what it means by blue. First, we need to test whether our model is free from multicollinearity problem. Then we use this technique, VIF. Okay, definitely you can use data. After you regress and have the output, then next you put the VIF. Okay, the VIF is this, and then you get this. Mean VIF is 1.28. If basically, if let's say the mean VIF less than 10 is still acceptable. If more than 10, we have the model is will have the model, we can say statistically have a big problem big multi-collinearity problem. This is what it means. Okay, secondly, the normality test. We look at JB. So in this case, I use that. I use EViews. Okay, I do not use STATA to make it short. Okay, we look at this. JB should not significant. In this case, it is significant, meaning to say that the distribution of the data is abnormal. So how to come up with the remedy? You need to increase your sample. I told you in this case, I just use a small sample. So you need to have, you need to use larger sample. In this case, I use 157 sample. It's still not enough. So actually, to do a survey data, 30 observation or 30 sample is not enough. Okay, we need at least 300 observation. Then we can get a good result. Okay, another one, heterogeneity test. It should be not significant. In this case, it is not significant, meaning to say that for heterogeneity test, this model is passed. Okay, so for JB, it is not okay. Okay, so the Ramsey test to identify our model, to confirm that our model is free from omitted variable, whether the chosen of the numbers of independent variable, including the control variable, is sufficient or not, is enough or not to represent Y. This is what it means by Ramsey test. So the Ramsey test must not significant. So in this case, it is not significant, meaning to say that the model is free from the omitted variable. In the same case, for this test, I use the EViews. Okay, other tests. Okay, you look at this EViews, Darwin-Watson. So Darwin-Watson is one of the most important tests to ensure there is no autocorrelation problem. Okay, so got two ways for you to determine, to confirm whether the Darwin-Watson test is passed or not. First, you look at the numbers of this 1.9, right? So the 1.9 here, actually, if let's say it is equal to 2, the Darwin-Watson test equal to 2 means that your model is free from autocorrelation problem. Okay, if let's say less than 2 got problem, more than 2 also got problem. But then if you want to confirm in detail, then Darwin-Watson has its own table. This is what it means. So for EViews, for Darwin-Watson here, if you refer to the law to say that it must be equal to 2, you need to convert the value of this Darwin-Watson into 0 decimal point. In this case, if we put 0 decimal point, consider as 2. It's okay. I mean, the model here is free. It's free from autocorrelation problem. Okay, so in this case, so but then overall, if we use OLS, we just have a problem. If you use this data, if you just have only you just have a problem of normality. The rest still okay. Get the rest to show that the model is in good fit. Okay, this is what it means. So if you use OLS, okay. Okay, now just now I mentioned to you one of the disadvantages to use OLS is that if we use the how can I say, the data in scale nature, either from 1 to 6, within 1 to 6, and we do not have much variety. Okay, and then the respondent just only can choose 1 or 2 or 3 or 4 or 5 or 6, not more than 6, not less than 1. Even there is the respondent also cannot give you the answer. Let's say example 1.5, 1.8. So this is the pro. If let's say your data is just only fixed at 1 to 6, actually the OLS have quite not that strong to capture this variable to compute the estimation. This is what I mean. That's why nowadays in the literature, many papers or many researchers have started to use this structural equation model. Actually, in the STATA, today I show you how we can do this structural equation model to use STATA. STATA also can use structural equation model, okay, to construct the latent, okay, the latent variable. Okay, example, this is actually the code. Okay, the first code, then you need to run y arrow y1 2 3 4 5 6 7. Okay, and then we put the dependent variable xa and then the control variable. So what is the structural equation model? Actually, the structural equation model want to show us, okay, that which instrument represent the most affect one factor, okay, or else, example in this case, which y instrument influence much dependent variable, in this case y. This is what it means. Okay, so that's the first step, and then second step, we can retrieve more information to use stat p effects, and the last one we go to the statistics. Okay, so I cannot copy the output in the slide because it's a lot, so I can show you here. So how it look like in the STATA, it looks like this. Okay, example just now, this is the code SVM. Okay, once you type the code, and then the data will give you this output. Okay, you see, this is the output, and this is the latent variable. Okay, after this, I will show you how to interpret it and what does it mean by this. Okay, the second command is this. Okay, once you type the second command, it will give you the information about the direct effect, indirect effect, and then the total effect. That is why this technique is called as structural equation model, because we can retrieve 3 stages of the result, or 3 stages of numerical behavior. Number 1, direct. Okay, direct effect. Second layer, indirect. The third layer, so that's why we call this technique as structural. Okay, and then the last one is this. So this is the diagnostic test. So for SEM, the diagnostic for SEM different than OLS. OLS just now, we have 4 diagnostic tests. The first one is normality test, JB. Second one, heterogeneity. The third one is Ramsey test. Then the last one is, just now, what is the last? Darwin-Watson. But then, for SEM, structural equation model, the diagnostic test quite different than OLS. These are the diagnostic tests that, what can I say, all of these tests should be passed, then our model is fit enough. This is what I mean. Okay, we go back to the slide here. I will show you the, in the slide actually got the, how can I say, the way to interpret it. Okay. Okay. From the mod, for the output from STATA just now, you can get this. Okay, you can get this model from model fit summary. Okay, this is the, how can I say, the diagnostic test that I mentioned to you just now. Okay, Okay, the RMSEA extremely poor fit. So why? So SEM normally need more sample. An ideal one 400, 400 to 500. 300 is still not that sufficient, but you still can try it. Okay, so that's why the result that I got here, the value for RMSEA extremely poor fit. Okay, what is the rule? You can refer to this. You see, poor. Okay. All right, and then the second test, CFI and TLI. Okay, the result that I got for CFI 0.099. Okay, the interpretation very poor. Okay, and then TLI negative 0.103. Okay, invalid. It should be this greater than 0. Dia tidak, it is not acceptable to have the value at negative, to have a negative value. We need to have more than one. Why? As I told you, the STM need big data. Okay, at range 400 to 500. Okay. Okay, the next test, the diagnostic test, SRMR. Okay, you look at the value for my SRMR 0.07 acceptable fit. This is the rule. It's considered acceptable so your model residual are modest despite the poor global fit. Okay. Okay, now what do all the result means just now? So I put it in this table. Okay, this is the way to interpret it. Okay, for this one, for the result for this level, okay, this is the first layer, and not the first layer. This is the global layer first. Then we go to we can disaggregate it at each layer. You see, education and income. If you refer back to the result that we got from OLS, it's consistent with SCM. So SCM also identify or also find that education and income significant with negative value. Same with the OLS just now. Okay, these are the way you interpret it. Okay, only education and income are statistically significant to cost Y with negative value. Okay, so now we look at the second layer. Now we look at this as disaggregated. So we look at the structural. Okay, this is what it means by this is actually the extra information that we will get from the structural the structural equation model. So instead, like example, if you use OLS, you just can you just can have this information. Okay, you can have this kind of information to cost Y as one factor, but then the STM will give you extra information, another information to say that to cost Y, which instrument will affect more. Example, just now, how can I say? Just now, statistically we can confirm that education and income, right, will significant cause change in Y. So from this model, we are able to know, since we know that Y have 7 instruments. Okay, Y have 7 instruments. From here, we are able to know which instrument, okay, will affect more. So in this case, we look at the biggest one, 3. Okay, this is what it means. Okay, this one, a global regression. So we can disaggregate into this. Okay, on a latent variable y, meaning to say that y itself, before we split into instrument, okay, still consistent with the previous result and also the OLF. Only education and income negatively affect y. Okay, this is the interpretation. Okay, so we look at indirect. Okay, we look at indirect. We look at how it indirectly influence. Okay, through influence the independent variable, the dependent variable using latent variable. Okay, still consistent with you. Okay, the way to explain is like this. Okay, XA and H are not significant, but education and income has significant indirect effect on all 1 to 7 indicators through latent Y. This is what it means. Okay, we can refer to this again. Okay, what? This. So, education and income, right? Able or significant to cause a change in Y, and we can have a look which instrument it affects the most. This is what it means. Okay, indirect. So this is the second layer. The third layer, this, the full impact. Okay, the first layer and the second layer, if this is the full impact. So how to interpret it like this? Okay, okay, education to cause Y to 7. Okay, approximate negative 0.1 to negative 0.23. So the stage is very detailed. Okay, this magnitude. Okay, actually, if you use the other software instead of STATA, okay, instead of the STATA, so actually you can draw a proper map to show from independent and control variable it will affect Y. So how this independent variable will affect the instrument? Okay, there is a software to automatically draw for you, but for STATA, you need to draw it on your own. Okay, for further information, you can try to explore, right? To explore papers that use SEM. You can see some of them. Try to draw in. Try to draw the result, okay, and put in the diagram to show what is the impact of independent variable to latent variable. So how this latent variable represented by the instrument just now. As I mentioned to you, in this case, we have 7 instruments for Y. So how this instrument will be affected from the independent variable. Okay, this is the finding summary. Okay, as I told you just now, right? Okay, this is the first layer on Y as a whole. Y as a whole, this is the result. Second layer, we look at how the variable, the independent variable, to cause the how can I say, the instrument that represent Y, the second layer. Okay, the third layer is the total. Okay, but then when we observe the result, we find that all consistent. But then again, what I can conclude here is that the numbers of samples is still insufficient. I need to increase more, up to 400 or even 500. Then I can get the variety of the result or more concrete result. Okay, because just now we have checked the diagnostic testing. Most of the diagnostic tests actually fail to conclude that our model is not in a good fit. So not to say the model, but then maybe we do not have enough statistical evidence to prove that, to show that, to support that our model is sufficient, maybe due to the small sample that we have. This is what we need. Okay, so that is all for today's session. I opened for question and answer. If you have any question.